Go.
Hello!
Hello, Mr. Ryan. How are you today?
Good.
Okay, so do you still remember what's ugly number?
Yeah.
Ugly
Not
number.
kind.
Not kind, yeah. So, what?
Mm.
So, yeah, it's a number that if it's prime, if it can be expressed as 2 to the power of a times 3 to the power of b times 5 times to the power of c. If a bigger or equals 0, b bigger or equals 0, c bigger or equals 0. So it's a positive
It all
integer.
has to be all prime numbers.
Yeah. If it's prime factors, only 2, 3, 5. For example, like obviously this 2, 3, 5 is a prime factor. Yeah, it's an ugly number. The first ugly number 1
Wait,
is a special
Does
case
it have
where.
to be? Does it have to be 3?
No, it doesn't look.
Yeah.
This is the prime. This is the ugly number. This is also ugly number because this is 2 to the power of 1. This is 2 to the power of 0. This is 3 to the power of 1. 4 is also ugly number because 2 to the power of 2. It's prime factors only 2, 3, 5. 5, 6 is it? 2 to the power of 6, yes. 2 to the power of 1 times 3 to the power of 1, right? 7 is 7. No, because 7 it cannot be expressed as the factors 2, 3, 5, right? So this is not ugly number, right? 8 is it? True or no? It can be 2 expressed as 2 to the power of 3, so it's a ugly number, right?
Yeah.
And 9, how about 9? Is it an ugly number, remember?
3.
To the power of 2, so it's an ugly number. So if it's a number, it's prime factor only 2, 3, or 5, right? It doesn't have to be 2, 3, 5 all together. It's just 2, 3, or 5. Then it's an ugly number, right? This is not, right? 10, is it an ugly number?
So
It's what? 2 times 5. It's an ugly number because 2 to the power of 1 times 5 to the power. How about 11? Is it an ugly number?
yes. I don't think so.
No, because 11 is the prime number, which is not 2,
3
3,
is a
5.
prime.
These are all prime number, prime vectors. That's what I'm saying. If it's a prime number that is bigger than, if it's a prime number that is bigger than 5, it's not a ugly number, right?
So
Because
that means
prime
6,
number.
7, 8, 9, 10, 11, 12, 13, 14, all of those numbers.
Does it make sense? Because we are asking the prime factors if it's only containing the 2, 3, 5. Yeah. Do you still remember how we testing it? How we check if the number is an ugly number? Yeah, we talked about this before. It's ugly. Yeah. N, right? If n smaller than 1 is 4, right? Alright?
Yeah.
And then now look, Eric. While n can be divided by 2, we repeatedly divided by 2, right? Yeah?
Yeah.
And while n can be divided by 3, we continue divided by 3, right? While n can divided by 5, we continue to divide it by 5. And then we just need to check return n equals what? N equals what?
N equals.
If we can divide it, if it's an ugly number, because we are these 3 means that we are repeatedly removing the if it can be if the prime factors can contain 2, we just keep dividing it, and 3 and 5 as well. So look, we can write this into a nice for loop. Yeah, for I in 2, 3, 5, right? Column. While n can divide it by I, and then n keep dividing by I, right? Yeah. So this is shorter. Yeah. You put this for I. Remember there are 3, 4, and then I put this using the for loop, and then I keep dividing it. What's the time complexity of this one? Oh what? Oh log n, let's say. Okay, log n. Okay. Yeah.
Log n.
Okay. Because we repeating it. Actually, yeah. Because it could be 2, 3, 5. So roughly in log scale. Okay. So how about if I give you this function and I want you to generate the nth ugly number. Okay, so this is today's topic. So if n equals 1, you should give me 1. The first ugly number is 1, yeah? N equals 2, you should give me 2. N equals 3, you should give me 3. N equals 4, you should give me what? 4. N equals 5, you should give me 5. N equals 6, you equals 6. N equals 7, you give me what?
7.
No, that's a trap. Come on, 7 is not an ugly number. Right? These are ugly numbers. So what's the next ugly number?
8.
Yeah. Does it make sense?
Yeah.
So you give me, I want to generate the nth ugly number.
Yeah.
So how can we do this?
I'm not ugly number.
How do we do? We keep generating, yeah?
Ugly.
So this is the proofing, right? So we're checking each number, yeah? And then we check each integer if it's an ugly number, then we reduce it. But there's a problem that because most numbers are not ugly numbers, right? Yeah? Because there are many numbers are not ugly numbers. So it takes time to check even those not ugly numbers, right? Right? So can we still write this as a proof of, right? Eric, look, define nth ugly, yeah, ugly number, n, okay? So suppose we already know that it's ugly function, right, Eric? So let's say the first number is I equals, let's say the first we start from 1, right? Then look, y something. Let's just write y2. It means that y2. What does y2 mean? Ended this loop. Always, right? But we'll break it. Look now. Look, if is ugly. Okay, we know this is ugly. I, right? If this number is, if I is an ugly number, then I need to n minus equals 1. I reduce n, right? And when n is equals to 0, what does it mean? It means that this I is the nth ugly number, right? Yeah? And then I can just return. Return what? I just said return what?
I.
Yeah. Okay, so look, if it's ugly number, if I is ugly number, I reduce n by 1. And then if n is equals to 0, and the current number I is the ugly number. Okay? Then every iteration, if it's ugly, and then what should I do here? Then I should do this. If it's not ugly number, I should do this I plus equals 1. I check the next integer, right? Alright? So look, if it's 7, if it's ugly number 7, no, then you will not count this part, right? You will keep adding. 8 is ugly number. I reduce 1 and check if it's n0, right? Does it make sense?
Yeah.
So look, if n is 100, you need to at least increment 100 times, right? But there are some numbers which are not ugly numbers. So you will keep checking every number. You will keep checking every number between 1 to, n, at least n, to see if all the numbers inside is an ugly number, right? The best case is all the numbers are ugly number, right? Right? Am I right?
Yeah.
Does it make sense? But there are some cases that like 7 is not ugly number, so you will not. If you still need to check if it's ugly 7. It's not. Then you will keep. If this is true, then execute this. But it's not 7. You will return false. So you will not go in there. You will go here, right? I will equals 1, then the next number will be 8, right? Until it breaks the loop and return, right? Here's the, because look, Eric, look, y something, y2, and then you say print hello, right? So computer, y2 do something, right? The computer will keep printing hello, infinitely, right? You will not exit, right? Yeah, because this is always condition, always true. y2 do something, it will keep doing.
And do a million
Endless
times.
this. No, more than a million times. Trillion, million. It won't stop because this.
10 trillion.
No, it's not a finite number. It's infinity, endless. Because that's what happened. True is always true, right? So here, why true? And when this loop will be exit, it's only the case when n it reaches to 0, right? Does it make sense?
Yeah.
Okay. So now, as you can see, this is not very efficient, right? Because we are skipping. We still need to check most not ugly number, right? So we can generate the nth ugly number using the other approach, which is what? Because look, the ugly numbers only contains 2, 3, 5. These 3 prime factors. Yes. All right.
Yeah.
So how about if we have a pool of numbers 2, 3, 5, and every time the ugly numbers, and every time we take the smallest, right? We take the smallest. Look, the first, okay, I show you. The first one is ugly numbers is 1, okay? And then I have a number to see the ugly number I have seen. This is a notebook, right? A notebook, yeah? Yeah?
Mm-hmm.
So look, the first ugly number is, look, now I need to repeat the n times for the nth ugly number, right? I take the 1, take the smallest from this pool, yeah? 1, yeah? And I remember here, this is ugly number, yeah? I remember, this is the number I've seen. I use this number to times 2, times 3, times 5, right? If they are not seen here, right? So that will be 2, 3, 5, right? And then I've seen 2, 3, 5 here, right? Okay, so next time, I need to take the smallest from this row, which is what? 2, okay. And then I times 2 will be 4, times 3 will be 6, right? Times 5 will be 10, right? These are all ugly number, right? Because every time I will take an ugly number and multiply it by 2, 3, 5, it's still an ugly number, right? Yeah? And I put it here, look, right? Yeah? Okay, now the second ugly number is 2, right? And now, 4, 6, 10. I need to put it here as well. 4, 6, 10. This is remembering. This is put it back, right? Multiply. Okay, so what's the smallest ugly number now? 3. I take it out. And times 2, 6, yeah? Yeah? But 6 is here, right? So I don't need to do anything. I've seen this before. Times 3, 9, right? 9 is not here, right? I put it here, right? And times 3 times 5, 15. Right? And 15, okay. Okay, so next one is 4. Alright? 4. 4 times 2, it's not appearing 8. 4 times 3, 12, right? These are the number I've seen, right? 4 times 5, 20, right? So you get it? Now I get the next one is 5, right? Alright? So we keep doing this. These, remember the numbers we have seen, the ugly numbers we have seen. These are the current ugly numbers we haven't multiplied by 2, 3, 5. So we're doing this n times. Every time we take it out, will be the smallest. Now what does it mean? We repeat this n times, then that will be the nth ugly number, right? Okay, I'm going to write this, okay? So the notebook thing, using, we can use the notebook as the set, right? Defined and ugly n, okay? Now I have a thing equals set, okay? Okay, so let's say first number, because we have seen 1, okay? And then the current ugly number will be, let's say data equals 1, okay? Look, do you still remember if we want to get the smallest number from a pool, what can we do? What kind of data structure can we use? The minimum, the priority queue and heap. Remember the heap, the smallest here, heap. Okay, so So this is a heap. We can say this is a heap. Okay, let's write it as a heap. Heap. And then look, we need to import a heap file from heap p import heap import what? Heap file, heap push, yeah, and heap pop. Okay, so this is the two functions we need to use to manipulate the list as a heap, right? Heap file is to, we can also import a heap file. Heap file function, so I will have a heap, and then I will have a list heap file. Heap file is to turning a list into a heap, right? And turning a list into a heap, right? And now I need to so look, for n times, right? In range, because we are going to do this n times. Right? And then look, we take a current argument number, the smallest current argument number from the pool, right? So we use the heap pop from the heap, right? So now we take this number and we put it into the scene value, yeah? Scene.add current, right? Then for I in 2, 3, 5, right? I need to multiply this current into the value. Look, new equals current times I. So this is the new argument number. But if it's not been seen before, look, if new not in scene, right? If not in scene, then I need to push it to the scene. Then I need to add it, right? This number I need to remember it. No, actually I don't need to. I just need to heap pop, heap push what? Push this heap, and then new, and then what was probably I can move this here. Scene dot add new, so I don't need to do it in two places here, and then I need to return current, right? Okay, does it make sense? Does it make sense? Not quite really, yeah. Sorry? Yes, I think so. I think that will work. He push heap new, yeah. Alright, look. The first argument number we know is 1. We put it in, we've seen it, and the pool, remember, 1. Yeah, this is the number of argument number we have seen. Yeah, yeah. This is the current heap. That this heap is allow us to get the current smallest argument number. Alright? Please don't do that. And then look, we repeat this n time. Alright? And you tell me what's this current heap. What does it do?
Save current heap pop heap.
Yeah. What does it mean?
It means that the current equals heap.
Sorry? What? So we are taking the smallest argument number from the heap, right?
And you put, if it's argument.
No, it's already argument number because the first argument.
You put it.
I multiply 2, 3, 5, and I put it in
here.
And here, right? Yeah. Look, if it's not seen, 2, 3, 5, and then the next one is 2, 3, 5. I take it out and I put it 2, 3, 5. Okay, so now you tell me what to do next.
You show.
And then next. So look, another iteration. Heap pop, right? Take away 2 because it's smallest. And then what? Multiply by what?
2, 3, 5.
2, 3, 5. So it's 4, 6, 10, right?
Yeah.
And I put it 4, 6, 10 here, right? As
Yeah.
well. And then the next one is
3
I take the 3 and I times it
by 2.
6, 5. That will be what? 3 times 2.
6.
I already
We
have
already
6.
seen it.
Yeah, here. And times 5. Times 3, 9. Right?
And then you times it by 5, 15.
Yeah, 15. Okay. So does it make sense? Yeah?
Yeah.
Yeah.
You
So-
just write in
Yeah.
5.
Okay. 15. Okay. 15. Okay. So look. So this will be more efficient. Why is that? Because we're repeating n times, and this is O1 constant, right? Because we're taking an element from the heap. It's O1 constant, right? Push and pop. Usually, yeah. And then look, sin. This is O1 constant, yeah. Yeah, does it make sense?
Yeah.
Why this is more efficient? Because we are not dealing with any non-ugly numbers, right? Does it make sense?
Yeah.
Look, the 7 is not here anyway. We don't need to check if 7 is an ugly number or not, right? Instead, we know that ugly number is the factor of 2, 3, 5. So every time we multiply 2, 3, 5, it's still an ugly number, right? Yeah. It's just how many 2, how many 3s, and how many 5s combination, right? So heap pop is O1 constant. Heap push may not be. Heap push, when you push something into the heap, it's actually O log n, right? But this does not execute it a lot, right? This does not execute it a lot. Okay? Yeah. Okay.
Any questions?
Any questions? Heapifies to turning into the list into the heap. Yeah. Heap. Do you still remember what's heap? Do you still remember what's heap?
You wrote that this.
Remember, heap is actually a tree, right? Look.
Yeah.
So every time, look. This is look. So it's a data structure, a tree that I don't know. Okay, I don't know. But the root of the tree is always guaranteed the minimum or maximum, right?
Oh yeah.
By default, it's minimum. It's called a min heap. Yeah, it's a tree min heap. Right. So look, I want to take one element from the top, right? So I know it's always the smallest or the biggest, right? Alright? Does it make sense?
Yeah.
Yeah, does it make sense? Yeah. This is the heap maximum maneuver. Okay, so I'm going to take a look. Okay, I'm going to erase these. Erase this.
For iron.
Okay, so you tell me what to do. Okay.
For iron.
Don't look at my notes. Okay.
For iron. 2, 3, 5.
Right, you write it. You write it.
I guess so. 4. While you're doing your work in the middle of coding.
No, I'm just looking into something. Okay.
For in. What do you think? I guess 2,
Yeah.
3, 5. Right?
Yeah. Yeah.
Any column or something?
Yeah.
Okay. Now what?
Now what? So what do we do there? For I, we multiply. If the number is not in the scene, then we need to push it into the left heap push, and then we also need to put it into the scene, right? We also need to put it in the scene, right?
In the bound.
Yeah.
How do we do that?
Or the scene dot what? Add. Remember? Scene dot add the new thingy. are we pushing we want to add common argue number is new, right? So we just need to add this to remember it in the new, right?
Yeah.
Yeah.
Add new.
Yes, in the add new. Okay. Yeah. Okay.
So
Add new with the bracket. Okay. Okay. So I need to correct something. So when we retrieve the value from the root, the root is O1, but if we want to remove it, it's O log n. The same thing as heap push. It's usually O log n, right? Because you need to rearrange the heap at some point, right? But why this is still faster? Because the numbers in the heap here is usually smaller, right? It contains the arguing number, right? It's the arguing number. It does not contain any non-arguing numbers, right? Alright? Yeah. Okay, so that's why this approach is much faster than the previous one. Because, for example, if there are many prime numbers which are bigger than 5, it's not arguing number. You still have to check it. Right? Yeah? Does it make sense? Okay, so can you say bye bye and see you tomorrow?
bye.